All right, here we go. So again, this is just a review from the lesson 5, the appearance of complex numbers part 2. So this is just kind of review. So when we add, we can literally just add up the real parts. So I can go 2 plus -7 and get what? -5. Then I can say 3i plus -4i and get -i. If you said -1i, I wouldn't technically count it wrong, but just know on multiple choice test that one's just not there. Again, also notice I did do the real part and then the imaginary part. So that is the correct answer. Any questions on adding? Pretty straightforward. Okay. Part B, it did look kind of confusing. If you didn't realize that I squared represented -1, you might distribute that and got I cubed, and then you're still in the situation with what is I cubed? What does I cubed equal?
I cubed.
-I. So you still would have gotten to the same conclusion because you still would have had -4 times -I and got to that same conclusion of +I. But hopefully you saw that I squared was really just -1 in disguise. And then -1 times -4i is just what? 4i. Again, if you wanted to say 0 plus that, you could, but you don't technically have to do that. Any other questions there? All right, so either way, even if you were to distribute, you should have got to the same conclusion. This one is a subtraction problem. It just happens to be that this doesn't have a real part. So what kind of gets nice here is if you wanted to, you could add like a 0 plus if you needed that placeholder. But if I have no real part minus a -2, what do I have? A +2. A minus and negative will make a +2. Again, if you need that, add that in. Then you have 3i minus 5i, and that gives me 3i minus 5i. Minus 2i or -2i. Very good. And then that's your conclusion. So this is like a minus. So you could technically take this and distribute. You could, yeah. There's technically you could put a -1 there. So, okay, that's fine. As long as you didn't multiply these two. You didn't multiply these two, did you? Oh yeah, you would only have to distribute to just these two. The 3i would not get affected. Any other good questions like that? So yeah, the minus will only go to the things like to the right of the minus sign. All right, and then we get into this one. I don't think we did a lot of practice on this, or maybe we did in the last couple of lessons, but we don't need to forget how to multiply. How do we multiply complex numbers? FOIL. That's basically the FOIL before we do the combined like terms. So what we'll do is we'll do 3 times -7. -21. Go ahead. Ask the question. Go ahead. Okay. Yeah. So when you're multiplying two complex numbers, FOIL or distributing or however you want to call it is the way to go. And then we do 3 times 4i, and I get 12i. Then you take -2i times -7, and you get +14i. And then -2i times +4i. Good. -8i squared. And then what do we know about that I squared? It ends up just being like a -1, which then ends up flipping the sign, which ends up making this a +8. I do write a little work there, but if you need to write the entire thing down again as a +8, do that. I like doing this because now I can just simply just combine like terms. But if you need that next step to write it down. So then here, again, I'm going to add my real parts first. So it's -21 plus 8, -13. And then what's 12i plus 14i? 26i. There you go. Questions on that? Again, if you have to write that next step to show that this needs to become a +8, do that. I just like writing my little extra notes there. All right, and then part E, where'd it go? Oh, there it is. I hit it too many times. All right, so this one, a same process. You're still going to FOIL this out. So -4 times -4 gives you what? +16. -4 times +5i. -20i. -5i times -4. +20i. And then -5i times +5i. All right. And once again, what's this I squared going to turn into? -1. And then a -25 times a -1 will turn into a +25. So now I'm ready to combine my like terms. So what is 16 plus 25? 41, right? 41, my bad. And then what's -20i plus 20i? 0i, or just simply, you can just cancel them out. If you wrote plus 0i, you're not wrong, but technically, this is all you have to write. This is what we're going to be doing today, is we're going to multiply something to basically get rid of the imaginary parts. And that something, I'll go ahead and give you the word, is called the conjugate. Is it a G or a J? This is now going into our notes. It's a J. Conjugate. I don't know, something like that. I don't take off for spelling, but the word is conjugate. It's basically multiplying it by a binomial in which it gets rid of the imaginary part. All right, so let's kind of jump into today's lesson. Like a magic word. It sounds like an English word to me. Ain't there a conjugate for English? Oh, but there's not a conjugate in English? I always felt like there was like this. A conjugate, when I think of the word, I think of it non-mathematical. I think of like the opposite meaning, or maybe a conjecture about the information that I have or something like that. But in conjugate here is where we'll actually do the opposite sign of the middle of the binomial. And I'll show you what that means here in a second. But I just thought that was what it meant in English, but apparently it's not a word. All right, so we are going to be in lesson 7. We're going to actually be lesson 7 and 8 are pretty much the same thing, just given more days to do it. And we're going to be talking about complex number division. It's the only operation that we did not see when we first brought this up. So complex number division. Bless you. And you always know the topic's going to be hard when it went from 1 day to do it to 4 days to do it. So just bear with me. I'm going to try to make this as clean and as smooth as possible. You might actually see it and go, wow, this is actually easy, until you get into it. And then you might see your problems that you might have. And then that's the problems that you just ask questions, work through it, and we'll get good at this. But we'll be working on this for 4 days. All right, so here we go. So in a real number situation, give me a real number. Perfect. All right, so let's take that 4. And if you're asked to find the inverse of that number, what does inverse tell you? Nope, that's opposite. What does inverse mean? Or another word, reciprocal. Cool. That's another word that people use. So when you hear inverse or reciprocal, what would you do with that number? If you're telling me negative, you're thinking of the word opposite. Opposite tells you to change the sign. But if you're asked to find the inverse of a number, or inverse of something, or the reciprocal of something, what does that mean? All right, here's my definition of reciprocal that I teach kids. Flip fraction. Now you might be thinking, well, that's cool. 4 is not a fraction. Is it not? It's 4 over 1. So if I take it and I write it as 4/1, which is the same thing as 4, and I ask you to find the inverse, knowing that it means flip fraction, what's my inverse of 4? 1/4. Right? So if I ask you to find inverse, that was all you had to do. And that's what we're going to be dealing with, but with complex numbers. So if I ask you, well, I guess let me pinpoint some out here. It is called an inverse because if I take the original number and I multiply by the inverse, you're supposed to get 1 out of it. So my question to you is, what's 1/4 of 4? Okay, let me re-ask this. It's 1, right? So 1/4 of 4 would mean how many times can you divide $4 into 4 sets? But let's say you just multiply this straight up like a fractions are multiplied. If you don't know this, you take your fractions, multiply it straight across. What's 4 times 1? 4. What's 1 times 4? What's 4 divided by 4? 1. All right, if you could see that that was 1/4 of 4 and the answer is 1, that's where I was heading at. But if you don't see it, that's fine. Just multiply the fractions as normal. So you know you found the correct inverse if the inverse and its original number does equal 1. That was a theorem that was probably taught in Algebra 1, Algebra 2, or whatever. But that's where this comes from. Yes. That is proportions. That's when you have a fraction equal to a fraction that you butterfly it. But if you have straight up multiplication, you go straight across. Yeah, it's like a cross multiply and divide concept. All right, so let's go into today's stuff. So if I wanted you to find the inverse of I, what would the inverse of I be? One over I. So the answer, these, well, they're my practice questions or what they have in the book here, but I'm taking this a little different direction than they did. Sometimes textbooks are great, but sometimes they want to go in a direction down like a rabbit hole where how they got back to the main point is a lot of roots in there when really we could have just walked over to the answer. That's where I'm taking you. We're walking we're not going to dig. We're going to walk there. All right. So 1 over I, right? And then you could prove this by saying I times 1 over I is what? 1, right? Which is correct. Now, technically, we don't like when I is in the denominator spot, which is the bottom of the fraction. So what I'm going to do is I'm going to get rid of it. I'm going to multiply by I, because what do I know 2 imaginary numbers will do? It will make a real number. But just like you learned in algebra, if I do it to the bottom to keep the number the same, I have to do this to the top. So I'm going to multiply I to the top as well. So I'm not changing the value of my inverse. It's still going to be 1 over I. But when I multiply by I over I, that's just a fancy way of me saying multiply by 1, right? Because what's I divided by I? 1. So I'm not going to change the value. I'm just going to change the way it looks. And a while ago, I told you, how do we multiply fractions? Straight across. So what's 1 times I? I. And what's I times I? I squared, which happens to be -1. But you know what? Let me write that fully out. I'll write it as I squared. And then we know that this is just going to be I over -1. Do I have to have the negative on the bottom? What's another way I could have written I divided by -1? I could put it on the side. I could write it as just negative I, right? When you learn about negatives and fractions, it can go in the denominator, it can go in the numerator, it can go right in the middle. But in this case, I don't really need the negative on the bottom. I divided by -1 is negative I. So the moral to this is the inverse of I is really negative I, which is where we get this conjugate from. I think I've spelt it 2 different ways already, but conjugate is the word. Bless you. So basically let me pause here. I want you to do the exercise number 1 on the next page. Just number 1. I just want you to find the inverse of 2i. I don't want to have an I on the denominator once you get your answer. How would you simplify it? That's exactly how it would start. Yes, sir. Now, how do we get rid of the I on the bottom? Ooh, you could do that. Just do that. Huh? You can. You can do whatever you want. As long as you do the same thing to the top. As long as what you do on the bottom, you do the exact same thing on top, you'll never be wrong. Huh? 4i what? There we go. Get you just process through that. So most of y'all probably did the first step within seconds. What's the conjugate? I'm sorry, I'm getting ahead of myself on words. What's the inverse of 2i? Just 1 over 2i. So we at least got to that point, right? Okay. The idea though is the reason we can't have an I on the denominator is because remember, I represents the square root of -1. And in the math world, it's actually incorrect to put a radical on the denominator. So that's why we're trying to move the I around because technically it is a square root, which is a radical. Now, I did here, you could multiply this by 2i, but I could also just multiply by just what? Just I. The goal is just to move the I, but you can do 2i or just the I. I'm going to do the I. And if you did the 2i, let's see if we get to the same conclusions. Again, multiply fractions straight across. What's 1 times I? Just an I. And what's 2i times I? 2i squared. And we know that I squared is equal to what? -1. So I get I over 2 times -1. And 2 times -1 is basically just what? Just -2. If you would have multiplied by 2i, you would have came to this conclusion. 2i over -4. What does 2 and 4 have in common? There you go. So then that would just go right back to I over -2. Yes, you would always need to simplify your answers. So that's what I'm saying. When you said 2i, I was like, you're technically not wrong. As long as we simplify, we can all get to the same conclusion. So either way there. Yeah, you did not do it wrong. If you multiplied by 2i, you did it just as fine as I did with just regular I, because we get to the same conclusion, right? So we're good there. If it's just a single complex number, we know how to find its appropriate inverse, right? What if it's like this? Let's go back to our notes. Let's say I ask you to find the inverse of this guy. So what is the inverse of 3 plus 4i? What's your thought process there? They're attached. Oh, that is amazing. That's exactly the answer. Wow. Don't know what happened there. Let's try that again. 1 over 3 plus 4i. The concepts don't change no matter how big the complex number gets. It's still just going to be 1 over that. But what's the issue? What's the issue here? What can I not have on the denominator? I can't have the I. But I can't just simply multiply by I. This is going to be a side note. You can write it so that you can see that this is incorrect if you want. But if I was just to take this guy and multiply it by just I, let's watch what happens. This will give me 3I. What's I times I? I squared, then I squared times, well, I squared is what? -1. -1 times 4 is just -4, right? Which is -4. The I squared would turn into a negative. But notice if I multiplied by just I still have an I. I haven't accomplished anything. So this is why we won't multiply by just the I. All right. But then how in the world can I figure out what to multiply so that the I would get canceled when I'm multiplying something by a binomial? Look at the opening exercise part E. And can you tell me what the difference was on those two binomials? Where? I know, but where was that negative and positive change at located? If you could give me like a description. Huh? In the what? The what?
Huh?
What did you say?
I was talking to myself.
Oh, if you could describe where the negative and positive change. Okay, I like it behind the 5. But if you had to just look at the binomial, where would you say it's changing? What's another word for that? Middle. Yes. So you're right behind the 5i, but not all of them are going to be 5i. So what I was trying to get at is you're going to want to change the sign in the middle. And that's all it is. So what we're going to do to find out what this answer is appropriately is the conjugate of, let's say, I don't know, let's call it just A plus BI. The conjugate of A plus BI would just be A minus BI. We're just going to change the sign in the middle and then FOIL it out just like we did on our warm-up. So when I look at this, what am I going to multiply 3 plus 4i by? Very good. All right. But what I do to the bottom, I still got to do what? I got to do it to the top. So what did you notice happen on part E? So when I look at E, wherever that's at, if I look at E, when I took these two binomials, were pretty much exactly the same, except those middle things changing. What did my final answer turn into? Huh? A real number with no imaginary parts left. So when we multiply by the conjugate, it cancels that imaginary part out. So that is why we're doing what we're doing. We don't want the I to be on the bottom. It can be on the top. It just cannot be in the denominator spot because we can't technically have radicals on the bottom. It's like saying that you can't have a period in the middle of your sentence. It's like it's not appropriate language for math. But when we do this work, the top part's super easy. What's 1 times 3 minus 4i? 3 minus 4i. So nothing happens on the top for now. But on the bottom, I need to FOIL it out. All right. So what's 3 times 3? What's 3 times -4i? What's 4i times 3? What's 4i times -4i? All right. And when we simplify this, what do we know I squared is? Good, that turns into a -1. -1 times -16 gives me a +16. And what's going to happen to this -12i and this +12i? They cancel out, which is great because we didn't want any more i's. And then we're left with 3 minus 4i over what's 9 plus 16? 25. Now, there are a couple things that this book wants you to recognize and a couple things I would actually want you to recognize. You don't have to recognize it. The math will always work out. Math will always math. But there's a pattern that gives you the answer every single time. When you are trying to simplify a inverse situation, when you have something like this, notice, what if I would have just squared my two numbers? What is 3 squared? 9. What is 4? Yeah, that's over that. What? Don't look at the I. What's the 4 squared? 16. What's 9 plus 16? 25. That works out every single time. Unless you don't see it. If you don't see it, keep doing it until you finally see the pattern. But the idea is anytime you multiply by the conjugate, the bottom number will just be the a squared plus the b squared. So we can actually develop a formula. If I want to know what the conjugate is of a plus I, it's really not just a minus bi, but if I want to know the ultimate answer where this ends up being, we know this is just going to be 1 over a plus bi. And then instead of doing all that work, I now can have an equation. If a plus bi is my start, its conjugate, its ultimate conjugate, will just be this guy with a change sign. So its conjugate will go on top. So this will be, not conjugate, inverse. Conjugate's what we did to multiply. Inverse. That's my bad if you're using pen. So inverse would just be a minus bi. We saw the conjugate just basically went on top. And then on bottom, the result will just be a squared plus b squared. Whatever my a term is squared plus whatever my b term is squared. So technically what you just did is we just saw a formula that works every single time when you're just trying to find the inverse of a complex number. It gets a lot different if there's something on top there as well. And we'll see some later down the road. Questions on how to find the inverse of a complex number? That's your answer. Your answer would be 3 minus 4i over 25. Now, if the question, and it usually always does, if I wanted this as a complex number, how would I have to finish this answer? All right, how's that look? There it is, 3 over 25. Yes, once I can write a 2 correctly. Minus 4i over 25. And that's perfect. So if it wanted as a complex number, we take our simple formula and we do have to split it up into 2 parts. The real and the imaginary. Any questions on that? So the only task I have for you today is just to do 3 through 7 on the exercise. If you finish that and you want more time on the other one, you can do that. But practice how to basically figure out what these inverses look like. We'll go a little step further on Thursday.